1, 2, 3. I'm Gabby.
And I'm Justin.
And welcome to the next episode of our cooking show,
Creamy Cool Chem.
It's so good.
Before we get started, make sure to have your safety goggles on and your lab aprons. Gabby, what are we making today?
We're gonna make ice cream in a bag.
What? In a bag?
Yeah. So first, we are going to measure out a cup of half and half.
Half and half.
That'll be good.
Take your 1 cup measuring tool and put 1 cup of half and half inside. Like this. Nice.
Okay.
And you want to have 1 cup per serving. Right now we have 2 servings, so I'm making another cup.
Okay.
Ah.
Now we
Simple. Open your bag.
tablespoons. Okay. Now 2 tablespoons of granulated sugar. Okay. Give me the other.
So now in these bags we have 1 cup of half and half and 2 tablespoons of cane sugar.
And now we need half a teaspoon of vanilla extract.
We have today no corn syrup added because you know we're healthy
They're
here.
all natural.
Mm-hmm. Oh.
Perfect. Ooh. No, just one happens.
Oh, see it.
Becoming ice cream.
Remember never to smell it like that. You gotta.
Waft.
Okay, ready?
Yep. Oh, that one's just gonna be a little extra vanilla-y, but
Vanilla-y.
That's fine. Sometimes there's percent error. So, and now we're gonna zip it up and make sure to push out any excess air.
Yes.
Okay, so now we need to put ice in our second bag. So we're gonna fill up this bag by 1/3 of ice.
Mm-hmm. So grab your
Nice ladle and scoop in the ice cream. And now we're gonna put a 1/3 cup of salt, which will help the freezing of the ice cream. Here's your
quick fun fact. When you add salt to the ice cubes, the salt particles interact with the water molecules, beginning the process of melting. But the lower freezing point of something, the more energy has to be absorbed in order for it to melt. Though it may seem strange, the moment you add salt to the ice bag, the water's temperature drops to a colder freezing point and it starts to absorb heat from its surroundings.
We're gonna place our ice cream in a bag inside the ice bag. Shake vigorously 7 to 10 minutes. Okay, we're gonna shake this for 7 to 10 minutes. We'll be back. Okay, so it has been 7 to 10 minutes, and we are gonna take out our ice cream now.
Oh wow!
Whoa!
And voila!
We have made ice cream. There it is. Ta-da! Cheers. You know, that's not bad at all.
That's actually kind of
That's
good.
actually pretty good.
feel free to add your favorite fruit or favorite snack into the bag. And you can make flavored ice cream, which we're going to make for you guys during class.
Yeah, watch as it becomes strawberry ice cream. So how did this work in chemistry? Well, to chemists, this process requires heat, like melting ice, and that is known as endothermic. So meanwhile, the water is forming in the bag is just as cold, that is below freezing, because liquids conduct heat more readily than solids. The supercooled water sucks heat away from the ice cream faster than the ice would alone, making it possible to make ice cream without the machine.
Oh, that makes sense. That really connects to what we're doing in class. Huh. Now, what are some implications for the broader society, Chef Gabby?
Well, in the broader society, this is a very quick way for supercooling and freezing. So I feel like this is a very simple way for people to freeze things that must be needed to freeze quickly.
Although ice cream may seem like a simple summer delight, the science behind this creamy concoction is very advanced. We have already inquired about the addition of salt into the ice and how it allows for the ice cream in the bag to supercool as the ice's freezing point drops and becomes extremely endothermic. We even noticed as we were shaking the bags that the ice bag was extremely cold, colder than normal conditions would imply. This is also an example of the endothermic properties of ice and salt, and why it's possible for the creamy mixture in the bag to cool so quickly. In addition to the supercooling process, the ice cream in itself is extremely complex. Under a microscope, it can be seen that ice cream is like a matrix of tiny fat globules, surrounded by air bubbles and ice crystals. In other words, ice cream is a type of emulsion, sort of like soap, where fats are dispersed through the water despite their incompatible properties. The fat needs to be prevented from clumping together by proteins from the milk. In order to achieve its smooth, creamy texture, these fat particles, ice crystals, and air bubbles must be very small. Therefore, the process of churning and time it takes to freeze the creamy solution is vital to making great ice cream, because allowing the crystals to grow more will generate larger ice crystals and a bad batch of the frozen treat. That is why supercooling the bag by using ice and salt is important, because we want to cool the ice cream quickly while also churning it and applying kinetic energy to it. As of now, there are potential innovations for the production of ice cream that could make this treat even better than it already is. Douglas Goff of the University of Guelph in Canada has investigated ways of introducing proteins in the plant winter wheat in order to reduce the growth of the ice crystals in the ice cream. This would allow for the production of ice cream to be creamier, smoother, and more efficient. Now, as you can see, food science is more complex than it may seem, and innovations for food are constantly being discovered in order to accommodate for the growing demand of such enjoyable foods like ice cream. Knowing the science behind foods can allow us to manufacture and produce them more efficiently. So the next time you get your next scoop, remember what you learned from Creamy Cool Chemistry about your favorite creamy concoctions.
Thanks for joining us today on Creamy Cool Chemistry. We'll see you next week. Bye.
Bye.